Thank you, Naomi, and everyone else. Kind invitation to come to CCA. It's my first visit, and I was very eager to come and see what it's like. And I'm very impressed with the CCA and all the connections with NYU and so on. And I thought I would give a sort of very general talk on what I think is some of the directions in what I would call extreme astrophysics. That's sort of using, if you like, conventional physics and pushing it to the limit. And I'm going to use this as an opportunity to float some trial balloons. So these are ideas that are partly worked out, but by no means all. I think this may be the first talk ever presented here where I don't have a single modern simulation to show you. So, but I think that the three topics that I've chosen to emphasize are ones that are ripe for sophisticated simulation. And if I manage to stimulate some of that, I shall have done my job. There's certainly ones with open questions that I think are resolvable. I should acknowledge various collaborators who I've been working with recently on this, and there's just a list. I won't go through them all. I'm particularly pleased to work with all of these people because they've all contributed in some ways without necessarily agreeing to everything I'm going to say. And I'd also like to start with another acknowledgement, and that is to Jim Simons, who has not only been the benefactor of this organization, but he kindly supported a Simons professorship when many of the ideas that I talked about, I was actually sort of working on those problems at that time. So I would like to pay grateful tribute to Jim Simons for his support at that, a few years back. Okay, so what I'm going to try and do now. So this is a slide that I use often in popular talks, and I'll use this here. And but I think it's also quite useful just to remind us of how large the scope is observationally nowadays in extreme astrophysics. I mean, we've got 70 octaves of electromagnetic spectrum, and I particularly like to go against optical astronomers who think they sort of rule all of astronomy, and they've just got one of these 70 octaves to deal with. And of course, it's a rather special octave for obvious reasons, but nonetheless, you have a large range here, and then you've got another 70 octaves now that are essentially opened up. And I think it's sometimes called multi-messenger astronomy, although the phrase is at least 10 years old, but it seems to have caught on recently. And I think there is a bit of a semantic confusion here as to, is a gamma ray, part of the multi-messenger, or is it part of the electromagnetic spectrum? And I don't want to take sides on that, but I do think those involved in public outreach should sort it out, because it is a little bit confusing if you don't mean. But I think most people now seem to think these are the additional messengers, and this is all part of the same thing, which is the way a physicist would think about it. Anyway, so this just shows how many different ways we've got to look at the universe and the sources that inhabit it. And as I say, this is using, if you like, what we would regard mostly as conventional physics, but pushed to the limit in exotic environments, rather than searching for new physical laws, which is the goal of much of contemporary cosmology. And so it's a very it's in some sense different styles. Okay, so in this talk, so I mean, and just to make clear about the range of energies for those who know SI units, which turns out to be not too many. So it's 1 zepto-electron volt to 1 zetto-electron volt. And of course, it goes up to yotta and what goes beyond that to get to the Planck scale. So there's a lot going on here. Okay, right. And so we've got 140 octaves to explore. So in this talk, I'm just going to talk on 3 topics, and I say float 3 trial balloons. And as I say, and I hope stimulate some interest among simulators and others. And so I'll talk about jets, cosmic rays, and fast radio bursts, because there are lots of things going on there. But before I do that, I should just say this isn't the extent of the field. This is actually a much longer list here. I just came from the head meeting in Monterey, and I'd say a few more things here, but obviously, unless you've been in deep coma, gravitational radiation you'll know about. You'll know about PeV neutrinos. There's almost as much hoopla about that. And this is possible identification with a blazar. There's neutron stars. This is all very passé now, but they radiate at 300 times the Eddington limit. I mean, that's a bit of an unsolved puzzle, I think. No, I'm going to talk about the ultra-energy cosmic rays, but in the intermediate energy cosmic rays, there's been an awful lot going on observationally, which means you've got to really up your game in trying to understand propagation and sources and so on. SS433, Hawke has shown 25 TeV gamma rays from this, and it looks pretty convincing, I have to say. I'll say a little bit more actually about that. Millisecond pulsars all over the place, now being found by the Fast Radio Telescope and so on. So, and there's a lot of physics as well as sources, and then the NICE X-ray timing observatory is producing a vast amount of data on particularly on neutron star binaries, on quasi-periodic oscillations, on flares from these things. Again, there's a trove of existing data out there and genuine discoveries, as you might expect. This is virgin territory for a lot of this, and people are making those discoveries. So there's a lot going on here. Okay, so these I say these new observatories. You know, astronomers love acronyms, so this is LIGO, Virgo, the Event Horizon Telescope. I'll say a little bit more about that. VLT and gravity. This is obviously the VLT, which has been around for a long time, but the new gravity instrument is transforming certainly the study of AGN, but much more. Beyond that, Fermi, atmospheric Cherenkov telescopes, water Cherenkov telescopes, new star. These are IceCube you know about. CHIME, that is also now coming online, doing low-frequency radio astronomy. It was meant to do cosmology, and it may yet do it, but what it's actually doing is transient sources right now, and in fact, it turns out that this may be its biggest contribution to cosmology, maybe through the transient sources. Auger, cosmic rays, AMS, also cosmic rays, and so on. So there's a lot going on. Okay, jets. So just a little bit, and I just wanted to just sort of call a few points out. This is Meerkat. One of the themes of this talk will be, you'll notice I keep mentioning telescopes that are all around the world and places you might not be aware of. This is Meerkat, which is in the Northern Cape in South Africa. It's sort of like a VLA there. This is I suppose you could call it, they call it this, but the Meerkat Deep Field, like the Hubble Deep Field. There's basically 2 billion sources if you multiply this over the whole sky. There's basically 2 billion sources there, and probably over half of those are jets coming out of black holes in active galactic nuclei. The rest may be sort of stellar activity. I mean, it's a little bit unclear at that level, but I mean, it's a billion jets basically out there, so they're everywhere. The Crab Nebula, this is a neutron star. Lovely to see our friend and colleague Val Ruderman here, and he certainly remembers this. And there's the pulsar right in the middle. Here's the blue is the X-ray emission from that with in the optical emission line filaments, but from Chandra, you saw this beautiful image, and you can see not only the equatorial emission from a sort of toroidal-like structure, but also the 2 jets that come out of it. So it's a neutron star, and yet it makes jets. This is the iconic image from ALMA of the protostellar disk, HL tau. What do you expect? A jet. There you go. It's there, the protostellar jet there. They're learning about that, and you know, as we speak. Here's SS433, one of the jets back from 1982 when it was first discovered. Again, this is now a TeV gamma ray source, prodigious one, and that's a real challenge because this is only a modest jet, quarter the speed of light, and it processes. I think I may even be able to make it. No, I can't. Thought I could make it process. Okay, it did before. Here's IceCube. As I said, there's PeV neutrinos and that, which may or may not be a blazar, but there's good. But we'll know very soon because we'll find more if these blazars are really neutrino sources. And then this is the neutron star binary, which you will all have heard about. For a long while, the observers were saying, well, we think this is a short gamma ray burst, or so they thought it was a short gamma ray burst, but they said we're not going to see a jet from this. And the radio astronomers were seeing nothing, and they said, well, shut up shop. It's it's not going to make jets or anything like that, which is because it's pointed in a different direction. So, but the radio astronomers were kind of stubborn, and they kept on looking, and lo and behold, it's got a jet. And it's expanding. So you see jets everywhere, and of course many more examples of this. So I want to talk about just about the observational problem a little bit historically. I'm going to use 4 examples. This is the first. I'm actually going to use Perseus A, but the first one historically was in 1988. It's the first active galactic nucleus at Lick Observatory, NGC 1068. 1918, Curtis, using again the same Lick Observatory, found the first jet, which is in Virgo A. This is another historical picture from Jennison and Dasgupta, the early radio interferometry. It wasn't proper radio interferometry, but basically they knew enough to show that this powerful extragalactic radio source had two components. And then about the same time, about a year later, it was shown to be straddling a galaxy, not on the galaxy, but on either side. And then here's the first quasar. It's often thought of as a discovery of optical astronomy, but it is a discovery jointly of radio and optical astronomy. And it was the radio that provided the position. And also, both of them, of course, found jets there. Both radio and optical in the discovery papers announced jets. So, and now we know that essentially every normal galaxy has a tiny nucleus which may outshine it, and massive spinning black holes orbited by disks launch jets in them. These are normal galaxies. We're not so sure about what's going on in dwarf galaxies, but that's basically the pattern. Okay, so let's go back to Perseus A. This is what it looks like now. These are the radio images. The black hole, or core if you like, is there, and then we've got a counterjet there. And one of the things you'll notice, and this is a pattern that's really become very apparent in the last couple of years, is that the emission you see quite close to the black hole is from a sort of boundary layer. It's from a sheath around the outside. And many of us sort of suspected this is what it would be. This is where the shear flow is, and this is where particle acceleration is efficient, and maybe also magnetic fields get amplified. But this is the feature that one sees. This is shown up in a little bit more detail. This is on scales of hundreds of gravitational radii. This one. This is also reminding us that in the case of Perseus A, you see these bubbles here. These are inflated by these jets, and they float up in the cluster. So we've got some idea historically how much power was made by these jets, because they make all this hot plasma which floats up in the cluster. It's not, in fact, a Halloween mask, but it kind of looks like two eyes in the mouth. But here it is. And so this already tells us that within the jets are formed, not as was once thought in the large galactic nucleus, but by this very tiny black hole in the center, 300 gravitational radii here. And they also have an enormously large environmental impact, which is important for cosmology, because this is both stimulating and repressing star formation and galaxy formation and the surroundings. So this has a large part to play in galaxy formation, these galactic nuclei. And of course, they make more power than the stars do. Okay. So here's Virgo A. There's a jet sort of shown there. There's the cluster which is formed. Here's a low-frequency radio image. You can see the jets, and again, you're inflating the bubbles in the surrounding cluster. This is the X-ray image jet from the center. This is on the scale of about 2 kiloparsecs. This is on a very long scale. These jets go out to hundreds of kiloparsecs, megaparsecs in some cases, but they're made by a black hole that's smaller than the solar system. So it's even more dramatic than the stuff that goes on inside an atom in terms of dynamic range. Okay, so this one we know, we can measure it. It's 6 billion solar masses. This is what it looks like, and I hope I can make this work. This is a movie made by Craig Walker. I don't know whether it'll... and this is what it looks like on the smaller scale. I'll come back to this, yes. This is what it looks like on the smaller scale. And basically, these are the published images. Is that one? No, it doesn't go. Oh, these are the published images, and they go down to scales of about 10 or with the eye of faith, 10 or 20 times the size of the black hole. You in published images are resolving down to that, down here. And so you can see that whatever is making the jets, it's within a factor of 10 of the size of the black hole. And I would argue that in this case, at least, it's actually coming from the black hole. And then I'm going to, not quite sure what happens next. So that maybe this will work. Is anything happening here? You know where this is. Oh, no, that wasn't there. Okay, so I was going to say that. So maybe I clicked on it, it'll do something. That's right. Click again. Yeah, click again. Okay, click again. There we go. There we go. Yes. Okay, so this was made by Craig Walker over 10 years of observation. There's actually better movies of this, but you can see you have the I'm really just advertising the capability to make these sort of time-lapse photography, and you can sort of see stuff going out, and you can learn about the dynamics of the jet on scales of, this case, of hundreds of gravitational radii. And as I think everyone here knows, the Event Horizon Telescope has taken data to do VLBI, the best ever VLBI images of the galactic center and M87 and some other sources, but mainly the galactic center and M87. And we don't know what, well, at least I don't, they may know, but I don't know what they found, but there's at least indications that they're going to tell us sometime soon. But they let me in the secret, so if you promise you can keep a secret, I'll show you what the image looks like of M87. It's like that. That's exactly what it looks like. So, but anyway, but the thing we have learned actually, it is announced, and it is be very interesting to see, is in case of Sagittarius star. I'm not quite sure what they're going to produce, but the gravity observations of Sagittarius star have prevented evidence, which they sort of basically believe, I think, that in the black hole, despite the fact we're in the galactic disk, we're looking face on to the black hole, looking along the rotation axis of the black hole, basically. So that's the gravity observations from the VLT. So anyway, we'll see. I don't quite know what the schedule of this, but I observe that at the APS meeting, there's going to be talks given by the leader of the project. So we'll at least find out something then. And on Sagittarius star and M87. And the hope is that at some level they're looking for the shadow of the black hole and things like that, looking for the gravitational effects caused by lensing around the black hole. And we'll see just how far they've been able to go with that. But this is the start of the journey, not the end of it, because people will get baselines to Greenland and things like that, so they'll be able to do better down the road. And so there's great optimism, I think, for that. Okay, so there's that. There we go. Okay, and Cygnus A, I said that's the Jennison-Skipper thing. This is what it looks like today. Well, this is actually looked like 20 years ago, but this is the X-rays in blue here, and then the red is the radio, the hot spots, which is where a lot of power is dissipated, the ends of the jets, where they go into the intergalactic medium, and then going down to the center. So I'm taking, you can see the jets there, you see a jet going across there, and that's what's fueling essentially the whole of these radio lobes. But if you look on the smaller scales, I'm concentrating on the smaller scales. This is, again, on the scales probably of several thousand gravitational radii. This is an image made by VLB by Bonn, led by Bonn, VLBI, and giant double radio sources. These are being powered by jets, and obviously eventually these become bubbles that float away. So 3C273, this is a quasar, of course, the first one. There's a galaxy there. You can see with the Hubble image, you can see the galaxy around it. Here's the this is what another gravity observation. So I'm quite impressed with these. This is infrared interferometry, 2-micron interferometry. It's another one, and this is a 3C273, and they're able to see. They look at the blue wing and the red wing of Passion Gamma, and they can see displacement across the sky. So they can see. They're starting to map out with real imaging the broad emission line region around 3C273, and that actually is relevant to what I'm about to say.
Physical scale?
Sorry?
What's the physical scale in that?
In this case, in 3C273, it'll be about 10 to the. They're resolving the broadband region on a scale of about 10 to the 17 to 18 centimeters. Okay, so you're out in that case, you're about 10 to the 4th gravitational radii. Okay, this shows. This is just a very old image. You see, 1977 to 1980. It goes 30 light years in 3 years. It's just superluminal expansion. It's just a kinematic effect coming along the line of sight. Freshman physics now, but it's indication that there's relativistic outflows, which we kind of know. Here are the gamma rays. They're rapidly variable. We know that many of these AGN show very rapid variability in the gamma rays, and this is a very key point that I want to make here. It's made somewhat better go to the. Wait a minute, I think I've lost a slide here. Bizarre. Okay, maybe it'll come later. Maybe okay. I'll make this point later. I thought it was earlier, but anyway. So the gamma rays are highly variable, and I'll say in timescales. In another quasar I'll show you shortly, in timescales of 3 minutes in the frame of the quasar. and that has enormous implications. But let's just continue with this. So the general picture that is emerging, and people are trying to simulate this in many different ways, is that we're dealing with a Kerr black hole. Of course, we'll get some sort of more indications if this is on the right track from the Event Horizon Telescope observations when they come. But this is essentially a two-parameter family of gravitational solutions, one of which is just a scale, and the other of which is the spin. You can call it A or whatever you want to call it. And there's a classical event horizon there, and not paying much attention to other possibilities that have been widely discussed, but it's just, I think, just classical GR. And you see them obviously in black hole binaries now. There's a three solar mass one just been made in the neutron star binary, probably, and 80 solar mass ones from the black hole binaries. So in the AGN, we see them up to beyond now 20 billion solar masses is the largest one claimed. Often the measurements of spin, I won't say how you do that, but the measurements of spin indicate they're spinning pretty rapidly in many cases, and the various ways of doing that. In the case of the quasars, at least, there's good evidence and reasonable expectations they're surrounded by accretion disks, and these accretion disks are inevitably magnetized objects. If you try and make them unmagnetized, it takes a few turns, and essentially dynamical instabilities amplify magnetic field. So you're stuck with magnetic field in one form or another in these disks, and so you can't sort of get away with ignoring that. And there are three types of accretion: low rate, intermediate rate, and high rate. The low rate has generally been, and I'll take some of the responsibility for this, been thought of as an ion-supported disk. I no longer believe that, I have to say. But the idea was to make some sort of funnel to get a jet started like that. And a lot of the simulations that are done are predicated on this model, but I'm increasingly suspicious of it in sources like M87. I'll come to that point in a moment. You also get thick disks when there's a high rate of mass supply, and that's when they're radiation dominated and their disks are inflated by radiation pressure. And then in the intermediate case, it's generally supposed the disks are relatively thin. I won't go through all the phenomenology of that, just to emphasize that you get magnetic fields. And in the case of the sources like M87, you can't really see any evidence of emission from the disk, so it looks like almost all of the power is liberated by the spin of the black hole. Up to 29% of the rest mass energy of a black hole can reside in the spin, and the typical efficiency of extracting it is about 50%. So you get as much energy out from the spin of the hole as you would from the accumulated accretion. So the way to do this, and this is just a sort of quick primer, if you like, on his Chandra, the Crab Nebula, a jet like that. And the general idea is just simply to make a unipolar inductor. Mal Ruderman taught us a lot about that. And if you flux that and an angular frequency omega like that, and a mass here like this, the whole thing's in place. That's really all you need. If you just say that use Faraday's law here, then you'll end up with a voltage which will give you a maximum energy of a particle that you could accelerate in that region. And then as everything's electromagnetic, the relevant impedance is that of free space, which is about 100 ohms. So, I mean, you could calculate all this sort of stuff, but this is essentially what it reduces to. And the power is the product of the voltage, and you've got some load there. And so you've basically got an internal resistance in the battery maybe, and then a load which is going to dissipate the power and accelerate particles for the gratification of astronomers and so on. And so if you go through all of that in simple ways, in a GRB, it's 100 zeta volts. It's 10 to the 23 volts, or 10 to the 14 GeV for particle physicists. AGN, it's zeta volts, and Crab 30 petavolts, and you already see in the Crab Nebula strong evidence that you're accelerating in the nebula particles to more than 10 or 20% of that whole voltage generated by the unipolar inductor, which is the pulsar in the middle. You're seeing evidence for particles. So at least 10% of that potential difference seems to be directly applied to particle acceleration. That's pretty impressive. So, and you can imagine the same thing happening in a black hole unipolar inductor. This is the only, this is the only simulation. It's a very old one made by my friend and colleague Jonathan McKinney, and there's much better and more sophisticated things done now, but it demonstrates you two things. One is you can learn from these simulations things that you would have thought of, and the second is that when there are doubts about whether or not mechanisms like this can really work, the simulations will do it, and of course there's much more sophisticated ones now. But in this case, of course, most of the power is being extracted from the spin of the black hole and used to power jets, and then the jets themselves are confined essentially by toroidal magnetic field that spins around them. So all you need is magnetic field, mass, and angular velocity, and then so you know in all these different circumstances, all the jets I showed you, essentially they're living off that. Okay, and that's the distribution of the toroidal field shown there. Okay, so this you might have noticed on the back of a banknote for those who still use such things. The normal way of thinking about these blazars is that you get two humps in the spectrum. These are the large spectra all the way from the low radio frequencies to the high gamma rays. The low hump is traditionally associated with synchrotron radiation, and the high hump is traditionally associated with inverse Compton scattering, Compton radiation. And the soft photons, either from the jet in the low power sources or from the outside, from the emission line region, the high power sources, are supposed to be made into gamma rays. Okay, that's the story. And I said there's trial balloons here and so on. I'm very suspicious of that. There's two reasons. One is that these Compton models, if you try and think about it for a moment, they basically say that they have to be in regions where the magnetic field is very small. And yet I've just told you that the way to get the black hole power out is to use use a strong magnetic field. So you should be magnetic dominated regions around the black hole. And and the way that actually works in practice, you've got to have breakdown of the vacuum in a magnetosphere around the black hole. There's a group here that Benoit Cerruti and Sasha Filipov and others are working on that have been able to make much more sophisticated models of this sort of process, but it's done in a magnetically dominated region. And yet the phenomenologists who are trying to interpret things like this as Compton scattering say, well, thanks for the magnetic field, we're grateful for all you've done with us. Now I want you all to go away in a non-dissipative fashion, so without us actually observing you going away. And as is the case with gamma ray bursts, I'm extremely suspicious that that really happens in that way. And so if you're in a magnetically dominated environment, you don't get this sort of dominant Compton scattering at gamma rays. So that's the other reason for being highly suspicious, as I said, is the gamma ray sources in the quasars have baryon timescales could be as short as 3 minutes. I'll show you an example in the slide that's got out of place in a moment. And sorry, yes, please.
Why do you not get Compton in the magnetically dominant? Because synchrotron cooling is so rapid.
Yeah, but it's a question of what is the radiation energy density in the radiation density relative to the magnetic energy density, and that's the problem. And a typical models that the phenomenologists in their one zone, it's an extremely lazy business observationally. They do one zone models, so in these one zone models, the ratio of the particle energy density to the magnetic energy density is 10 to the 4th sometimes. So I mean, but it's not a one zone. Think about a one zone model of the sun. There's a 6,000 degree black body. And then you say, it's a bit of a puzzle getting all those neutrinos, isn't it? I don't know what's going on here. So you wouldn't do that. And you shouldn't do that in these jets. You've got a huge range of physical conditions along them. Anyway, so the problem, of course, and this is the QED we trust. I mean, we may not believe all the meteorology of accretion disks, but well, you can doubt QED in astronomical environments, but it's probably not a good career move. Essentially the gamma-gamma pair production, so-called Bright-Wheeler process, is about a fifth of the Thomson cross-section. And we know in the quasars, the BLX, it's not so clear, but in the quasars, there are photons there. We see them. That's the reason they're quasars, is because there's a vast amount of ultraviolet radiation there, and you can't avoid it, and you can't get a gamma ray, however you make it, out through that porous. So that's the real puzzle, and I'll come to that in a moment. And there's another problem, actually, which is it's a work problem in Landau and Lifshitz, although many of us were pleased when we discovered it. I certainly wasn't the first, but and there's a theorem you can't get a gamma ray synchrotron photon more energetic than essentially 1 over alpha times mc squared. And so that's a limit to essentially the energy of a gamma ray photon. And it's 100 MeV or thereabouts, and yet we're right up here at many TeV energies. So that's a real problem. So these are two serious problems here. And what I think is, well, I'm going to advocate, this is a trial balloon here, is the protons can be accelerated to PeV, more than PeV energies in the zettavolt potential differences. So they can actually be accelerated these enormous energies without radiation loss. And then they make secondary electrons in a shower, and they make these pairs, and essentially they're made through the beta, that's not black hole, it's beta Heitler cross-section, and there the cross-sections, the fine structure constant times cross-sections is smaller, but it doesn't matter. That's a good thing, not a bad thing, because you can get up to high energies. And and you make the electrons as secondaries, but before you make pions are not very good because they lose a lot of energy because they make neutrinos and so on, so they're not very efficient. But these are very efficient because all the energy has got to get out eventually when it can. So that's the story. And so I'm going to say that that's synchrotron too. Not always, but I mean, it's a multi-zone model and there's different zones and so on, but a lot of it is, the stuff is actually synchrotron. And this is 3C279. This is just what I should have shown you earlier was that the timescales, it's 5 minutes in our frame, the most rapid variation, and 3 minutes in the frame of the source. So that says that, if you want to do these things at enormous radii, you've got to appeal to a lot of relativistic magic, and to get much more rapid variability. It's out to 10 to the 17 centimeters or something, and you get things varying, like months radii, and you get things varying in minutes. So I'm actually going to claim that they come from much closer in. So how do I do that? So here's the disk, the cartoon thereof, and the thought is that these emission line clouds, which occupy a very small fraction of the volume of a quasar, are in fact originate in the disk around here. They're clumps of gas that are confined and flung out by centrifugal force along essentially a jet-like direction and illuminated by radiation from the accretion disk. And then I'm going to just tell you that the gamma rays come from within the jet, from somewhere like that. So the problem has been is that the ultraviolet radiation from the disk and scattered by the clouds and so on will stop those gamma rays from escaping. There's a huge opacity to them. And so what I'm claiming, and I'm not sure that this works, but it looks promising so far, is that a relatively small amount of mass flung out as a sort of sheath around the jet just will absorb the ultraviolet radiation just like it does in a molecular cloud. And so this, in fact, is free of ultraviolet radiation. And as long as the gamma rays aren't too energetic, and there may be one case when they may be too energetic, I'm not sure yet, then if you're looking directly down the jet, not from the side, but you're looking directly down the jet, then gamma rays can escape because all the ultraviolet radiation would otherwise prevent them from escape has been very efficiently absorbed by a small amount of gas. So that's the story. And that's one of the trial balloons. I'll float another one here because one of the big puzzles always along is why is it that 5 to 10% of quasars are so-called radio loud objects, the remainder are not. And it's true for AGN across the board. The CFITs and so on are essentially radio quiet objects. So radio quiet means not impressive jet. Maybe some bipolar outflow, but not an impressive relativistic jet. So what's going on there? And here's a thought, and this is something that I don't know whether Yajia Yuan has got here yet, but she's been simulating this, and we're learning sort of along the way, is basically the thought is that if you imagine magnetic field and gas being supplied at sort of Bondi radius, about 10 to the 5th, 10 to the 6th, sort of radius, sort of GM over sigma squared, if you like, that sort of radius out here. And there are two modes of supply. And in something like an elliptical galaxy, it comes in at all latitudes. But in a disk-like galaxy, it'll come in mostly equatorially. And the contention the conjecture, if you like, is that in this case, you retain magnetic flux. And so you retain magnetic flux by this sort of a cylinder, if you like, this cylindrical walls here. But in this case, it's easier for the flux to escape because it can keep on reconnecting and getting out. And so in this case, it's a high flux region, that's a low flux region. The spin of the black hole is clearly insufficient to make a jet, because we know lots of these CFETs have spinning black holes. So that's not enough to make you a jet. But if you have a flux and a spinning black hole, and furthermore, the inflow in these disks concentrates the field at the center. Typically, you expect B going as 1 over R in this region. Then you can make a jet that's quite efficient. So that's again is another trial balloon, if you like, as to whether, I don't know whether this can work in practice, but otherwise there's not very good explanations for why some sources choose to be radio quiet and some radio loud.
Is that supposed to be just the very inner 200 gravitational radii that is in?
No, okay, important point. That's the gravitational radius there. This, think logarithmically, is GM over sigma squared, where sigma is the one-dimensional velocity dispersion. Thanks for clarifying that. So that's typically 10 to the 5th to 10 to the 6th gravitational radii. And it's basically where the gravitational potential is changes from being dominated by the black hole to being dominated by the stars. So, and that's the sort of way you expect, in fact, you see in these radio jets, you see that's a very important radius because it's where the nature of the pressure confinement changes, as you might expect, and that leads to structures in the jets, which you can observe.
Yeah, I can understand the jet one on the left better than on the right, so why is it?
Well, okay, the thought is if you bring in the gas and perhaps try and drag field with you equatorially, then these field lines sort of lie on the disk like that. And it's then very easy for them to reconnect and sort of the flux can escape. If you hold them vertically.
Why wouldn't gas come in from all directions?
Oh, because this is in the case of the radio quants, it's more of an equatorial inflow. It's like a spiral galaxy. So the gas is coming in equatorially, much more equatorially. We see these disks on those scales. Sorry?
They're very tiny relative to the size of a spiral galaxy.
Yeah, it's small compared with the size of, but you can see there's equatorial inflow. This is the conjecture is that in these cases where you've got large amounts of angular momentum in the flow, you make a sort of disk of gas. You know, in our galactic center, there's a molecular ring at 1.7 parsecs. And so you can see again a ring of gas there. So ours is a particularly feeble AGN. Don't be ashamed of it. We wouldn't have lived near quasar. But it's the gas is, so there's a ring of gas we can see there.
So you say that's typically seen in radio loud and radio quiet?
The presumption, well, the CFET galaxies, which are a large class of AGN, basically don't make jets. Right. And they're mostly associated with spiral galaxies. It's not quite like particle physics in that the phenomenology is not clean, in the sense it's more like sort of zoology, and there's always exceptions and so on, but it's basically, that's generally the pattern.
But wouldn't you expect the thing on the right to apply to the situation on the left, where things are coming in from different angles, but essentially you get the same disky sort of inflow?
Well, no, I think what's going on, what looks like, and both you know, in the observations and the modeling, is you don't get such a the angular momentum is much less in this case, and so it doesn't make a disky flow. I mean, it could be wrong. It could be this can be, like many things, can be shot down both observationally and theoretically. But if you think this is a somewhat troubled explanation, you want to try some of the others. So yeah. But anyway, I mean, you know, the one that people had was it was just a spinning black hole, and then we learned 20 years ago that the black holes without jets are spinning very rapidly. I have to be careful here because I've got colleagues and friends who are on opposite sides of the debate. But I will say, yes, I am pretty persuaded. Mainly, the thing that has given me more confidence are the very beautiful reverberation type measurements that have been made that are interpretable in terms of it's essentially the broad ion lines that and the widths of them, and if you get broad lines, then the disk can get close to the black hole. I think they've been a little over-interpreted by some of the enthusiasts, that I will certainly subscribe to. But I think the general pattern that CFETs have rapidly spinning black holes, I believe that. And so I don't believe that can be the parameter that determines radio loudness. At any rate, onwards and upwards. Okay, so, and those who know this business about FR1s and FR2s, the weak jets are the ones that don't make it out through this interaction radius GM over sigma squared. They just become bubbles and plumes. And the powerful jets are the ones that keep on going on. Similar things, obviously, in yeah. So a little bit about particle acceleration. I'm doing, yeah. Okay, particle acceleration. There's now there's been a lot of work done here, and Benoit and others have done a lot of work on reconnection and so on. I'm a little bit worried about that for just for the flares. I think these magnetic. I'm saying we've got magnetically dominated jets, or we get stripe winds from pulsars and things like that, and so we've got a lot of electromagnetic power, and that's got to dissipate into particle acceleration. And reconnection is A, unavoidable, and B, a benefit, because it's an explanation for the high energy particles that you see. But I'm going to meet with my colleagues, but I'm worried that it can do this fast enough to explain the flares. And I think you're getting a large amount of magnetic flux processed through a very small volume. It takes time, and I'm not sure that it can do it fast enough. And I'd like to sort of advertise an alternative possibility, inspired by, sort of topology. This is knot theory and so on, and one of the great persons in knot theory was Alexander, who described knots by polynomials. Here he is. And he is using a military solution to the Gordian knot, and he's got his axe or his sword there, and he's going to use a military solution. This is reconnection, so not a very subtle business. But the thing that I know from my childhood is that the myth of Alexander and the Gordian knot was accompanied by a giant electrical storm. So the whole business, which is one of the proofs of his deity and all of that. So that had to be a good clue. But the alternative thing, I think, is that if you imagine magnetic fields, and it's not a bad metaphor, as hairy ropes. So they're made of strands twisted as strands and sort of magnetic fields straying out of them and so on, like you would see, for example, on the sun. And if you imagine that they naturally break up into this sort of braided type structures, and then in the way that they're going to tangle themselves up in the Crab Nebula, in jets and everywhere else, they're going to go entangled. And then they can certainly reconnect by resolving, say, there, but they can also just untangle themselves without a major change in topology. And that can be done at the speed of light, and that can lead to a large sort of speed of light crossing time dissipation of magnetic energy in this region. So I think that to see whether this can be simulated and works in practice is something that I'd love to see, and I just sort of throw that out as a possibility for something to try. And you might say, well, how are you going to get particle acceleration out of this? Well, as with the rope, a sailor gets burns on their hands and so on with ropes, and so it will be friction at the surface, and that friction is almost certainly, I think it's essentially in the electric shear stress between two ropes moving past each other. And that can be a good particle accelerator. And instead of having the fuel lines cross each other like that, they slide along like that, the flux loops. Instead of going in like that, they go like that. And that can lead to a lot of just as much dissipation of magnetic energy, but can give you proton acceleration if the trained protons there, and the gamma ray emission through the sort of beta Hartley process. So that's the plan. Yes. Somebody said.
I just feel like I got lost track of what I don't know the term magnetoluminescence.
No, well, I invented it. So, yeah, a while ago. Yes. What's it?
Of the various phenomena you were describing to us, there were like the blobs on the jets, and there was the crab, and there were quasars. Which topic is this?
Well, I think for all of them, essentially where you are delivering a large quantity of magnetic energy or electromagnetic energy to a larger volume, then ultimately you know that's going to dissipate. And in the jets themselves, let's take them as an example, you imagine you start off when it's electromagnetic, at least I imagine, and then it becomes hydromagnetic as it entrains gas from its surroundings, and so it becomes baryonic plasma and so on. And by the time it gets out to those hot spots, say in Cygnus A, I kind of imagine that it's probably mostly gas dynamical, Most of the energy is in the bulk kinetic energy of the plasma, and then it passes through a strong shock, which means it can accelerate particles by a shock front. Shocks don't work in magnetically dominated regions. That's why people appeal to reconnection.
But what domain were you foreseeing this?
In the magnetically dominated region, say, imagine the Crab Nebula. Imagine you're supplying a huge amount of magnetic flux, far more than the nebula can handle, into the nebula. Then that has to dissipate into the high-energy particles whose emission we see. So that's all of that. And one way of doing it is to have the field lines reconnect, swap partners, like that. The other way is to have them without a major change. That's a change in topology. Without a major change in topology, just have them untangle. So the same amount of flux can occupy less, can have less mean magnetic RMS field. And so that loss of magnetic energy then goes into relativistic particles. And the mechanism, I would say, it's basically the friction between different magnetic ropes that is the source of the particle acceleration.
And this is right near the base of the jet?
No, well, in the case of the Crab Nebula, this is out in the nebula you can see. In the case of the jet, this is going all the way along it, but especially in the places where you're seeing most of the emission coming. So that's gamma rays in particular. Yes, okay, good. Good, this is good. It doesn't matter if I don't get to the end of this talk, because the next part is even less believable. So go on, yes. To whose work?
Louis Tao, T-A-O, who was at Columbia.
Physics, yes.
Yes, and he made the argument that once the field gets strong, you can only tangle and wiggle it so much because the magnetic tension fights back. So we're in the strong field limit. You've already said that. We have to be to produce all this energy. And so the field's very, very stiff. It's hard to tie it in knots. I don't know how to tie it in knots like that.
By having, well, partly you've entrained gas. You've got energy
Sure.
in the bulk and energy in the fluid. It's not like a tokamak plasma or something that's basically at rest. It's one that's moving. We know it's moving at relativistic speeds.
But it's still a low beta plasma. So even though it's moving,
high sigma, because you know these things are moving with the Lorentz factors at least at 10.
Sure.
And some people claim thousands. I mean, that's
sure.
There's no evidence for
but
that.
how
They claim that.
that doesn't?
No, that's a huge amount of relative energy between the inside and the outside of a jet.
Okay.
And that's
so
the difference from having a sort of a solar situation or a tokamak where the thing, the zeroth order thing is at rest. It's that relative kinetic energy.
But
either
since
electromagnetic
it's all super alphanic, that's going to suppress any sort of like Kelvin-Helmholtz wrapping or something, isn't it?
No, you get relativistic Kelvin-Helmholtz if you just do a simple fluid calculation.
Okay.
This is not go in my youth. You can get Kelvin. It's interesting, but you get Kelvin-Helmholtz instabilities there. Yeah. And yeah. Okay. Great. Yes.
Are you invoking still the Crab flares as hadronic emission from accelerated protons? I missed the last point that you had in that slide.
Yes and no. I'll give an accurate answer. And yes, we are considering this as a possibility. Yajie is behind you in here. Yes, considering this as a possibility. I think, as I say, I'm floating trial balloons here. So I would say that it's possible to use the beta-Heitler process in SS43 and the Crab Nebula and so on. But do I believe fervently that that's the case? No, but we're certainly thinking through ways of trying to make this happen.
The energetics is sort of like interesting for, let's say, neutrino production in pulsar nebulae, if this is the case?
Okay, if I'm trying to be an astro engineer and do this as efficiently as possible, then I want to get in the rest frame of the proton energies below 140 something MeV, which is the threshold for pion production. As soon as I start making pions, then I've got these neutrons who are lazy, good for nothing things, and neutrinos, which are even worse, and so they're carrying away lots of energy. So the idea is that you accelerate up until what photons you have, provide radiation drag and hold you below the pi. If you're into full-grown pion production, then you're going to have to need more power to explain things. That's the way I would see it. But I'd say this is a work in progress, with the emphasis on progress and work more than work. But we're thinking about it. Okay, all right, good. Cosmic rays. I've got not much time left, but that's all right. So I've got 10 hours, 24 minutes left. Okay, good. Okay, all right. So cosmic rays. So the change of pace. So this is, there's the spectrum. There's Victor Hess, who was a very brave man who went up in his balloon, and he was totally confident he would return to Earth. And here, of course, we see, no, I've got to use this one, I've told, yes. I think I blind people with that. So GeV to ZeV, and you get measurements up to about a tenth of a ZeV, but at source, because there's losses going on, at source they're probably pretty close. They have to be pretty close to a zeta electron volt. And so there, for particle physicists, don't want to make a big point of this, but there you are. And this is Auger, one of these miserable places that astronomers choose to work. And, you wouldn't know what that is. I thought I'd change that slide. Okay, I was going to put some disreputable slugger from the Yankees here, but I thought that would cause a problem. But anyway, so I forgot to change that. But it's the same sort of thing. Anything you hit in sport is about the energy of a cosmic ray, the highest energy cosmic ray, or that's the momentum. The particle physics is not always able to make the distinction between momentum and energy because for them it's the same. But here you go. So where are we? Okay, so the source is low energy. It's things like obviously in the heliosphere. Supernova remnants look like being the dominant source up to the knee, up to below petaelectron volt energies. Then the sort of traditional things that are invoked for this shin, if you like, of the so-called shin of the spectrum are things like pulsar wind nebulae. And the highest energy, as we've already seen, you've got the available potential differences, double radio sources, and so on. I'm actually going to try out the trial balloons here in this work I've done with several colleagues, including especially Naomi here. The idea is that some of this may come from shocks around galaxies in that region, and here you've got clusters of galaxies that are responsible. So that's the alternative that we've been looking at. So I'd say a little bit about that. So here's some data, and I'm not going to go through this. Naomi has talked about this here, I know, and Glennis has done a lot of work in this area. I just want to make a few sort of salient points, nothing very much. The first is that the spectrum, certainly the Auger observations, are telling us quite a lot. There's these so-called ultra high energy cosmic rays, which are here, the ankle up to the toenail clippings of the universe right up there, and then and two other things. One is that without getting too detailed and going into this, it looks like as you go from there to there, you're going up to higher Z's. So it's conceivable that the quantity you really care about, which is the rigidity, the momentum per unit charge, so these things are going around the magnetic field, momentum per unit charge, the thing you really care about, that is all the same, but as you go to higher energies, to a large extent, it is you're going from, say, protons to iron, for example. And there's more said. And the other thing which looked like it was important was that there's now a convincing, I think, measurement of the dipole anisotropy. And again, nobody's talked about this recently. But if you allow for the fact that the galactic magnetic field will deflect the particles as they come to Earth, the pole of the dipole can be shifted, and in particular, it's not inconsistent with it being in the direction of the Virgo cluster, which I already showed you in an earlier slide, in the one around M87. So I'll just make that point there. Now, here the mechanism for particle acceleration is diffusive shock acceleration, which is Lorenzo Cerrone here and others have done a lot of work on, and basically the idea is you get particles rattling backwards and forwards across the shock front in a sort of low sigma environment, if you like. And then the bottom line of this is that if you have magnetic turbulence accelerating the particles, then you transmit a power law. It's a sort of simple statistical mechanics argument. and it relies on the self-excitation of magnetic instabilities in the vicinity of the shock front. And this is for non-relativistic shocks. And I'm not going to go through any of the details about this, but I quite like to think of it as a magnetic bootstrap, whereas the escaping particles trying to escape upstream make the magnetic turbulence that is responsible for confining them. But some of them will escape upstream, and that's what's important. So here's just a cartoon with rather a lot of information on this. So the idea is basically that there's a cluster of galaxies, say in this case the Virgo cluster. It's obviously more complicated than this. It's surrounded by an accretion shock that surrounds it, and then in between the green and the red, there's an inflow of velocity, inflow of gas towards the cluster. So it's going through this high Mach number accretion shock, and the gas is being compressed, and the cosmic rays that are escaping from the galaxies in this zone here, it's more or less the scale, we're over here, the galaxies that are escaping in this region, some of them do actually escape upstream. And the contention is that those are the highest rigidity cosmic rays. And this is the source of a large fraction of the ones that are actually measured at Earth coming from the corrected direction. And to do this, you have to make the magnetic fields be twiddled micro-Gauss in this region here, made by the particles themselves, but very below nano-Gauss in this region here. And there's a much more sort of complicated story to tell, but this is the essence of it, so with large Larmor radii and so on. So you can spend a long time being accelerated there. And then when those few lucky particles that escape upstream then are able to get to Earth very fast before losses destroy them. And so there's obviously other, you may go out to 50 or 100 megaparsecs for other sources, but the Virgo cluster is the closest one. And it's interesting that might be a source of a good fraction of the highest energy cosmic rays. And so there's a termination shock there. So there are other sort of details in this sort of general picture, but this is the sort of, if you like, the trial balloon that I'm thinking about here. So that, in practice, of course, it wouldn't be something simple like a sphere. Again, this relates to simulations, because there are these, I don't know whether people here are associated with the Illustrious and other simulations. If there are some people, this sort of approach can be put into the Illustrious simulations that have real filaments in them and have real models of how gas would actually assemble into clusters. And there's other types of shock around. And I think in principle you could, once you've got a theory right, it could be put into a sort of global cosmological simulation. Okay, so there's that. And so here's just a general idea. As the galaxies inject, say, PeV cosmic rays, which is what escapes from our galaxy, and then they get re-accelerated up to exavolt rigidities, and they propagate more or less ballistically to Earth, and they're observed in that form. So at this point, I have 2 minutes and 36 seconds. I can stop. No, well, I mean, but I'll do this extremely fast. And if you won't actually notice what I'm saying, I hope, because it doesn't make any sense. Okay, fast radio bursts, they're kind of interesting. In fact, I remember giving a talk at Berkeley not long ago, and Elliot kindly asked me what I thought they were, and I told him, and I gave a sort of talk about this length, and I still have the same answer, but it means I haven't got anywhere. Okay, so anyway, so when these are now sort of, for a long while people thought that they were anomalies or so on, and microwave ovens or whatever, but now they're real things. They're extragalactic. In the last few months, there have been announced 250 of these things. Some of them are repeaters. There are a few that are repeaters. They're now seen down to 200 megahertz. One of them, at least one of the repeaters, shows intrinsic pulse widths that appear to be resolved down to 30 microseconds. They come from the other side of the universe, about 1 minute or so. There's a lot here that's being learned as we speak. This is a subject that's growing as we speak. So the energies are probably 10 to the 31 to 35 joules times some beaming fraction. Brightness temperatures, for those who care about such things, which are pulsar radio astronomers, are 10 to the 40 or more, which means you've asked the wrong question, I think. It's a bit like the cosmological constant in Planck units. You've asked the wrong question. And they're highly polarized. They're sort of like pulsars in some sense, but they're not pulsars. The repeaters, and there's 2 classes. Well, this is astronomy, so there'll be 5 classes, some of which have no members. So these are the rates. So this is sort of, one per 5,000 years per bright galaxy, roughly. I'm not going to go through, I haven't got time to go through all the details of this. All I'm saying is that the telescopes that are being used to observe this are being constructed like mushrooms, and the telescopes are cheap to do this. It's low frequency radio astronomy. You get it for Radio Shack. It's the signal. It's the back ends and the signal processing. That's where this takes the art of radio astronomy to the max, and it's lovely what they're doing. And so we're going to learn a lot over the next few years. Here's a repeater. As I say, sometimes, in some cases, it'd be every few minutes. There's some repetition with every few minutes. And so what are they? These are some of the models. They're ET, as you know what that means. So this is in a sort of it's descending conservatism, I suppose. And I think all dark matter annihilation, of course, everybody's got to get in that. So soft gamma repeaters, galactic nuclear pulses. So I believe in the magnetars, always have. So they're basically magnetars. And so the point is that, it's a strange business, but in a relativistically spinning superfluid and superconducting nuclear matter with a 30 times the quantum electrodynamical critical field, this is the boring and conservative explanation for what's going on. So, I mean, we have to come to terms with that. So at any rate, so basically the thought is that, it's a QED playground or whatever, and we've got about 30 of these things, and we know the magnetars themselves, and there's now very good evidence that they are these strong magnetic field pulsars, with, in this case, relatively slowly rotating, and they release magnetic energy rather than rotational energy, and they flare as soft gamma repeaters. There's a large phenomenology associated with this, which I shall not rehearse here. You sometimes see radio from them, and sometimes you don't. The thought here for the gamma ray bursts is that they're essentially quakes or flares on the neutron star, the surface of the neutron star, and that makes a pulse, essentially a linear wave, if you like, in the magnetic field lines. And the basic idea is that the pulses that go down the open field lines that get out, essentially, I think, let me not just go, okay, what am I going to say? Okay, I thought I had, I'm just trying to do this fast, but okay, so this is the story. No, this is the story, so maybe I'll go back, but this is the story. Essentially, you start off with, which is roughly a linear mode, and it has to be a linear mode because otherwise the whole thing will create different pairs and times locally. So the vacuum is essentially a perfect conductor. You can create all the charges and currents you need. And essentially, a force-free electromagnetic pulse goes along the open field lines, and it's a bit like cracking the whip as you go down the density gradient. You get the amplitude goes up. It becomes nonlinear, typically at about 10 stellar radii. And then at 1,000 stellar radii, it converts into an electromagnetic wave. So this is an example not of having some synchrotron maser or something like that. This is, I'd like to call post-Maxwell, pre-J.J. Thomson electrodynamics. So it's just electromagnetic fields and currents and magnetic field, nothing to do with coherent or incoherent particle emission. You just have as much charge as you need. And the idea is, do these waves then steepen, like Indiana Jones or something? Do they steepen as they go down the density gradient? And I thought they did, and I had a good argument for it. But Yaji Yuan is here, showed that, in fact, they don't steepen. The waves don't steepen. So this isn't the way to make a sort of 100-meter pulse of magnetic disturbance into lots of 10-centimeter Fourier modes that you would then mode convert into electromagnetic waves down the gradient. And so we're looking at other schemes for doing this, and I can't claim that we've demonstrated this, but in some sense the metaphor, if you like, for this is something like a hydraulic jump, where this is, water from a faucet, and you make this feature like that. You can see it in rivers and so on. And this is a turbulent wake downstream from a disturbance, and that turbulent wake makes high-frequency eddies and so on, and those would ultimately mode convert to electromagnetic waves as they escape from the magnetosphere. And that's where the radio pulses come from. That's the story. a long way from having demonstrated that. Again, this is ripe for simulation. So let's just finish there. Won't go on to that. Propagation, I will emphasize this and say the propagation effects are likely to be very important here. A lot of what we see may not. There are some features that are, I think, fit with this model. I haven't got time to go into them, but some of them will be imposed. And the bottom line may well be for cosmologists that these are extremely important as probes, even more interesting as probes than they are as sources in their own right, rather like pulsars have been. And so you may well, obviously these things are things that are very much works in progress, so they may well tell us a lot about probes and so on. So, and again, there's a lot coming down the pike, and so that's the end. Okay, thank you.
Thank you, Roger. So, questions? Can you use the microphone, which is, you just pressed the...
What are your thoughts about...
Use your seat mic, please.
Well, I'll repeat the question. Okay. What are my thoughts about electron acceleration in supernova remnants?
And specifically, some colleagues who work on this, I think, are concerned that when we can actually measure the energy in cosmic ray electrons produced by supernova remnants, it's smaller than what's needed to explain the galactic population of cosmic ray electrons.
Okay, maybe I should just back up a tiny bit for those who don't know. There's quite a bit of circumstantial evidence that the protons that are the dominant cosmic ray spectrum are made by shock waves through this diffusive shock acceleration or some variant of that at the outer shock fronts, blast waves of supernova remnants, say 1,000, 10,000 years old or something in the galaxy. The electron production is less than the ion production by at least depending on how you measure it, but at least an order of magnitude, maybe 2 orders of magnitude, depending on how you measure it. But still, it is a bit of a challenge because it is easier to make the ions than the electrons in the more sophisticated models we have now of cosmic ray acceleration. So I would say my own view is that we don't understand the injection of the electrons well enough to be confident that it fails. It's not such a big problem. But if it is turn out to be a problem, then obviously pulsars are a source, and pulsars have been invoked, in the dark matter story as well. So I would turn. I say there are other ways of making electrons. The major energetic problem, about few percent of the galactic power goes into cosmic rays, basically. Mm-hmm.
Why don't we see fast radiant bursts from SGR flares with this model?
I thought about that. I think that they're in a different energy regime, but what you've got in the SGR flares, I think, are much more energetic disturbances on the closed field lines. And the way you get the gamma rays is the waves going backwards and forwards along the closed field lines. And those are very efficient. When you get above essentially the Swinger field in some frame, then you can make pairs at will, and those will make gamma rays. What I want to do is to have a lower amplitude wave disturbance going out along the open field lines, and then converting to radio waves without going through this prodigious production of gamma rays. Because as soon as you start making gamma rays, the wave mode damps out immediately. And I think that's what happens in the SGR flares.
In a way, you want a weak...
It starts off with a few percent amplitude at the surface of the star from either a flare or a quake, and goes out down the open field lines, and then becomes delta B over B, becomes of order unity at 1. But at that point, when you've gone, your magnetic energy is now 10 to the 12th Gauss at 10 stellar radii, you're no longer going to be above the quantum electrodynamical critical field, which is 4 times 10 to the 13 Gauss. So it really has no alternative but to continue as an electromagnetic disturbance supported by just enough current as it needs to supply the curl of the magnetic field.
So the way you think that SGR flares are too energetic?
I think they're the more energetic cases, yes. And so these are ones that are that don't do that. They're the more common ones that are just smaller flares. and smaller sources.
So I think, sorry to...
Yeah, no, it's good. Yeah, these are important points, yeah.
Observational progress ruling out your model or confirming it would come from just observations of galactic magnetars to look for fast radio bursts during those flares.
I actually think that is a good way to go, and I say independent of what I've claimed here. I mean, it's an obvious thing to do, is to stare at the known magnetars, the known gamma ray magnetars, and see if you see flares from them. And I think the observers know that, and they're doing that. I mean, just like they look at the repeaters, they should look at the regular magnetars, and they're doing that as far as I know. Yeah, sorry, yeah.
For the fast variability at the base of the jet, there's still timescales that are way sub-horizon. So I was wondering,
yes,
what gives you the Doppler factor to shrink the typical variability timescale in the model that you have? Or you have some beaming of the particles themselves that is not bulk?
No, I think you have to appeal to Doppler factors. Just to emphasize what Lorenzo said, if you've got three light minutes is, maybe at least 10%, most 10% of the size of a black hole in, say, 3C279. So it isn't a question of being small; it's a question of being really small, and so you have to appeal to time travel effects as you go along the jet, and you only see this when you look along the jet. That's my claim. You only see from deep down when you're looking exactly along the jet. So you've got a real opportunity for getting, gammas of 10 would suffice. It's just I'm uncomfortable with gammas of 1,000 at 10 to the 17 centimeters, which I think is much harder to stomach. But that's a prejudice. But again, this is both theoretically and observationally contestable. I mean, one of the problems is there's one quasar that produces may produce variability above 30 GeV. That means that you can't absorb out photons below 13.6 electron volts by having some plasma there. You've got to be Thomson thick or something to take that out, and so seeing the high energy variability is a challenge to this. So I think that's one of the ways that it's confronted by observation. All of this is confronted by observations, I think, and so if any of it works out, I shall be thrilled. Yeah. Hi.
Hi. So I think we talked about the single zone models of lasers, and you say that this has definitely some problems to actually try to understand the photon emission. So, but how would you approach the multi-zone models? Because then it's also very, very complicated when you want to consider like leptonic and leptohedronic models in different zones. And how would you connect them? How would you consider the criteria?
Well, we're not at that point yet, but I could imagine EHT-type observations telling us a lot more about jets and their interactions with their environments, and starting to put in those boundary conditions, if you like, in the now pretty sophisticated hydromagnetic and electromagnetic models of jets made by spinning black holes, and in the case of quasars, the disks around them, and sort of slowly edging your way towards that and inferring a particle acceleration prescription, perhaps inspired by imaging of what's going on in these jets, and then asking what you would see. But I think, we already know from all of the observations I showed you that at least down to about 30 times the gravitational radii, there's emission going along all the way along them, and particles are being accelerated all the way along them. And it seems strange to just imagine there's only one radius where the emission comes from. I mean, people did have a sort of half of a reason for doing that, but I think the observations are quite contrary to that. I think you're getting emission all the way along these jets from 10 to the 13 centimeters to a megaparsec in the extreme cases.
But it's kind of hard to distinguish different photon sources along the jet, on the disk, outside.
Yeah. And again, and I think I've only made it harder by saying that the external photons may well be wiped out by absorption. So yeah, it is. But I think that's going to be the challenge.
Right. Okay.
Yeah, it's, but the observation is getting better and better. Okay. Thank you. Yeah. Sorry for going on too long. Yeah. Okay.